in the last session, we had the introduction to VLSI and the ASIC flow, FPGA flow, and just we had started the synthesis, synthesis inputs outputs, the overview of synthesis. So today we will continue further, more deep dive into synthesis process. So this specifically the logic synthesis, okay, the logic synthesis. So we will clarify about other synthesis, the physical synthesis, all those things actually. So today's flow is about logic synthesis. Okay, Shravan.
Yeah. Good evening, everyone. So today I'll be taking the session on the synthesis complete flow and what are the inputs that are needed for my synthesis process and what are the outputs you generate or you get as an output from the tool when you do a synthesis process. So just a quick recap of the previous session. Uh, as you guys know, the synthesis is nothing but the process of conversion of RTL code into a gate level netlist. So when you give an RTL code to the synthesis tool, the output you get is an gate level netlist. So the format of the RTL and the gate level netlist might be of Verilog or VHDL format. So here is a small example, like when you give an input of such RTL code, you get an gate level netlist as such. So here they have assigned some AND gate, OR gate, and XOR gate. So by that you can make it out. The output Verilog netlist looks something like this. So this is the replicative scheme input files to generate the tool, to generate the gate level netlist. So first of all, what is the file is obviously the RTL file. So the Verilog RTL code that you want to convert into gate level netlist have to be given for the tool. Next are the libraries. So to convert it into a gate level netlist, it has to have some file where all my gates are predefined so that the tool can pick whatever gate it required for the operation or for the conversion of the uh, logic that you have written in your RTL code. So we need a library file for that. So I'll elaborate this file description in the later slides also. As of now, these are the list of inputs and outputs we get in a synthesis process. So the other input is a library file, and we need to give some timing values because the process of ASIC implementation on the complete backend flow is only dependent upon three parameters, that is timing, power, and area. So SDC is a file where we define the timing optimization constraints, power optimization constraints, and area optimization constraints of the RTL code. So these three are basically the inputs of the synthesis process. Now next, as an output, what we get is the gate level netlist, the converted RTL code into a gate level netlist, and the outputs are the reports of timing, power, and area. And we get an SDC output file also that we'll be giving that SDC file later for the implementation of the physical design. So these are the inputs and outputs of the synthesis process. So let us get into each and every input, what each and every input file contains. So these three are the inputs, that is library, the Verilog file, and the STC file. So first, the library file contains the gates. So basically, gates are defined from previously from the library vendors itself. So you will get a standardized input file from the foundry where all the functionality information and the timing information of that file will be of the gate will be defined in that file. So that is what I have defined here. A library is a set of standard cells and their defined characteristics and parameters. So a library is a set of standard cells is nothing but a set of gates, and it will have the defined timing and functionality information in that particular file. So a standard cell is a pre-designed layout and layout of specific basic logic gates. If you were in the previous session, there was a flow called analog flow or full custom flow, where they implement the basic building blocks of SOC. Those are nothing but the logic gates. So with that particular flow, they develop this gates they develop this basic gates and they generate some timing information for that gates. So it will have a combination of both combinational and sequential cells. So the combinational cells are nothing but inverters, buffers, and NAND and NOR gates, multiplexers, and the sequential cells are latches and flip-flops. So libraries are usually given by the library vendors and unique to each foundry and technology tools. So the parameters which are defined in the library are given by the library vendors itself. So whatever foundry, like it will be different, the library format will be different for each and every technology nodes. That is, if you take 130 nanometer technology, the library parameters like the timing values in that particular file will be different. And when you come to the lower nodes, that is 14 nanometer, 28 nanometer and 45 nanometer, the parameters defined in that particular library file will be different. So when you come to the technologies, it is the nanometer technology that we are defining here. So these are the basic building blocks of SOC. So here we are only using the timing information and functionality information. There are some backend views also of the libraries. As of now, we are not using that, but usually libraries also will have front end and backend views. Those are nothing but the layout formats of the library. So that we'll be using them in the later stages. So it also has some particular information about area, power, and delay of the each and every cell. So in a descriptive way, in a total way, if I have to tell what is a library, it basically consists of timing and functionality information of each and every gate. So just a reference of 45 nanometer technology library. Usually a library will have about 800 cells, which includes the following cells. So the following cells are nothing but the simple combinational cells. Those are nothing but the basic gates and complex combinational cells. So there might be a logic in your RTL where it needs some complex gates to be converted. So that complex gates are nothing but a and or inverter, that is AOI, and or and inverter, and some adder circuits or multiplier circuits that will come under the complex combinational cells. So in the sequential list of cells, there will be flip-flops, latches, and scan cells. And MISC cells, you'll have buffers, clock multiplexers, and clock inverters. So these are the types of cells that will be present in your library file. Okay, so libraries include all front-end and back-end views. What does this say? Okay, so as I told you, here we are using a logical library, but when you go to physical implementation of that particular cell, you need some back-end views for that cell also. That means you need the metal information, you need the structure of that, and you need the pin information of that particular cells. So in the later stages, we'll be using this back-end views of library. But in a synthesis stage, you just need the conversion of gate. You don't need the physical implementation of that gate because you're not performing physical design at this stage. So when you go to the later stages, you can use that libraries of backend type. So coming back again to the list of cells. So under the combinational cells, you will be having these as the different types of cells, and for each and every cell there will be different types of inputs. There will be different types of inputs and outputs attached to it. So different drive strength and fan out. So if a cell is with x1, that means it is having x1 drive strength, and the fan out is x, that means it can drive one gate at the output of that particular cell. So it will have different types of inputs. It will have driving capacitances or the driving loads at the output in different variations, that is x1, x2, x4 and x8. So this all combination will be present in a library. So when you consider a complex combinational cell, for this also you will be having high fan out because the when you combine or when a complex cell is there, like an AND or inverter, it will be having high load capacitance at the output pin. So it might drive some 8 inputs or 8 outputs at the input pins and output pins of that particular cell. So that is the advantage of complex combinational cell. Basically you can give the input or output pins a high load. So these also you'll be having in multiple variations, like x1, x2 and x4. So those are nothing but again the drive strengths, how many gates it can load or how many gates it can drive at the output. So yeah, what does we mean about the fan out? So fan out is nothing but at the output pin, how many output gates we can.
Shravanti, you
Yeah.
continue on the slide deck. I think Jagrut is anyway answering all these questions. In case if
Yes.
some things are missed out, I'll take care. So let the
Yeah.
flow continue. Okay.
Yes. Okay. So when you come to the next category, that is buffers, clock buffers and inverters. So in the same way, you can see the different variations of drive strength. So a clock buffer is nothing but when you give a clock signal at the input of a buffer, that particular buffer which is accepting only clock signal at the input is called as a clock buffer. So basically, this is used when you're doing clock tree synthesis in the later physical design stages. And the advantage of this particular clock buffer's usage is it will have equal rise time and fall time, so that we'll not get any violations or any timing issues in the later stages. The gate level netlist will include clock buffers in the clock paths also. So clock buffers are nothing but which will take an input as a clock signal. So coming to the category of sequential cells, so under the sequential cells, again you have latches, flip-flops and scanned flip-flops. So latches is a level sensitive cell, and it will have again two types of cells. One is active high and active low enable. Next is the clock gating cell. So clock gating cell is nothing but when you want to stop the propagation of the clock, you can just give that clock gating cell as an input, where when needed only clock cell can be propagated into the circuit. So there might be some issues in the power with the RTL, where you need to insert this particular clock gating cell to optimize the power. So in such cases a clock gating cell is inserted in the circuit, and it will be made on and off according to the logic that you want to propagate the clock. So it is basically a oning and off in propagation of the clock signal. Next is the flip-flop. So we have both types of flip-flops in our library file, that is positive edge and negative edge triggered, and multiple combinations of sequential asynchronous reset, synchronous reset, and both the types are present in this particular category, and there might be flops with two inputs, I mean to say the two outputs, that is q and q bar. Also that type of cells also will be present in the library file, and according to the combinational cells, the drive strength, as I mentioned, x1, x2 and x3. For the flops also, that particular category will be there. So different drive strength variations of the cells will be present in the library file. Scan flip-flop. So if there are any logic that a scan enabled signal have to transfer to the D input of your flop. So if that particular logic is there in your RTL, in such cases, it needs a scanned flip-flop. So if that particular logic is there, it has to pick some scan flip-flop gate in the library. So if you can see the diagrammatic representation, the scan flip-flop looks something like this. So basically, there are three types of library models. That is the timing models, whatever values, the delay values it is picking for the particular gates, it is dependent or it is based segregated on these particular library models. So the library models are three types basically. One is a linear delay model, the other is non-linear delay model, and concurrent current source model. So based on this particular the cell delays, the particular cell delays of a gate are segregated and calculated according to this timing models. So there is some other load models also where you consider or where you calculate the resistance and capacitance values of that particular gate. That particular load models is called as wire load models. So now again, there is some other parameter that we need to consider, that is process voltage and temperature. So depending upon the operating conditions, that where you want to work this chip or handle this chip, in which kind of environmental conditions that you need to like manufacture this chip, according to that conditions also the delay values of the cells varies. So a library model considers this process voltage and temperature conditions also, and it will depict the delay values of that particular cell, and uniqueness and edge sensitivity of the timing parts. So uniqueness, it is nothing but it will define the signal sense. So if it is a right transition, it is a positive unit, and if it is a fault transition, it is a negative unit. So the signal sense also will be defined in the timing models itself. So how a library file looks, I mean to say how the cell is defined in a library file. It is segregated in particularly in this format. So the timing data of the standard cells is provided in the library for such kind of in the such kind of format. So first, the library file will have a library model. So as I told you, like the operating conditions, the process voltage temperature conditions, where the chip is going to manufacture or where it has to function, that and all conditions will be there in the first section of the library. That is, the name of the library is defined, and the operating conditions, wire load models and lookup tables, those are nothing but the delay tables of that particular cell will be defined in this particular section. So if you take in this library, name of the library is given, and the cell name, next is the cell name. So if you take an example of a AND gate, the cell name is defined as AND gate, and the cell level attributes such as the transition timing tables or the delay timing tables of that particular cell, and the functionality and the area how much it is going to occupy when it is physically implemented, it will be there in this particular cell section of the library. Next is pin. So for a cell, if you take an example of an AND gate, there are two inputs, A and B, and the output, let us take it as Y. So for each and every pin, let us take an example of A pin. So for each and every pin, the timing, power, capacitance, leakage, and other characteristics of each pin is defined in this pin section of the library. So once this is everything is declared, the closing of this particular information is done. So this is how the format of the library file will be. Okay. Now, how the delay value of a particular cell, or the how the timing value of a particular cell is calculated. So usually in the previous like old in the old ages and all, they used to run this spice level netlist, and they used to depict it in the transistor level, and like they used to give some input voltage to that particular transistor levels and calculate manually how much that particular cell is taking time to travel from the input pin to the output pin. So as the technology got improved, that particular way of calculating the delays in the transistor level have become difficult. So they got into another models called as timing models. Those are nothing but the library files in present we are using, that is nothing but the linear delay models, non-linear delay models, and CCS timing models. So it was way too difficult when they were calculating the spice level netlist model and depicting the values of timing values of each and every cell. So they got into this timing models where they have already declared the values, I mean to say declared the delay values of each and every cell, where you can just interpolate and pick the value that you want for the optimization of your the timing power area of your netlist. Now, can anyone address in the chat box like what is a cell delay or a propagation delay?
Propagation delay is nothing but 50% points difference from input to output.
Okay, more?
So
Yeah, propagation delay is nothing but uh, in how much delay it is taking to travel from input to output through any gate. The gates
but 50,
that is
Okay,
50% points are reference point.
that is.
yeah,
I think
yeah. So, yeah, like whatever you have addressed is a partially correct. So when you want to calculate the timing value, that means input at the input pin of the cell, how much time it is taking to generate an output or to depict an output, that time is called as propagation delay or cell delay. So once an input is given at the input pin, the time it is taking to travel at the output is called as propagation delay. So that delay value is that delay value is calculated using this timing models, whatever we have discussed previously, that is non-linear, linear, and CCS timing. So for every timing arc, so the timing arc is nothing but when you consider this inverter cell, at what you want to calculate delay. So I'm giving an input at A pin and I'm getting an output at Y pin. So this particular arc where it is traveling to get a delay value is called as a timing arc. So for every timing arc, wire, or it might be a wire, or it might be a gate, we need to calculate propagation delay and output transition. So these two values, these two timing values are calculated in the timing models. Now, the delay values, how it is calculating is, it is calculating with the help of input net transition. So, as I told you, it is dependent upon the input pin. So, at whatever the input net transition is there, according to that, and output load. So anywhere, any of the timing model, the cell delay is only based upon the input transition and the output load. This is very important. Like a cell delay is a function of an input load and an input transition and an output load capacitance. So usually in nowadays, like we are using this non-linear delay model. So this is how the nonlinear delay model is taken. So the driver models are nothing but the input cases, whatever we are taking. So the input at the input side, whatever is there, the voltage sources and the fixed drive resistance. That means the pin resistance at the input side and the ramp voltage source. The ramp voltage source is nothing but the transition value at the input pin is taken as the input driving model, and at the output whatever we are getting is the maximum capacitances or the minimum capacitance according to that particular input ramp voltage source is given. So when you consider an non-linear delay model, the two values we are depicting is input net transition and the total output capacitance. So LU is nothing but a lookup table, a template where your delay value you are taking in the range of 5 cross 5. So your input transition and output net capacitance you are taking for the value variation of 5 cross 5. So the index 1 is a input net transition and index 2 is the output capacitance or the output net capacitance. So for this particular values, what will be the delays of my cells? So here they have took an example of cell inverter where the pin Y is my output pin, and the rising and the rising delay values is depicted according to this particular values, this particular range of values. So how it is selecting a delay value? Now, if I want a delay value, or if tool wants the delay value of this 0.147955, where it is giving the range to optimize the timing for that particular cell in this particular range. So, as I told you, it is a 5 cross 5 matrix. So, the first value of this and the first value of this will be tabulated in this form, cell delay table form. So if you see in the left hand side, that is input transition and the output load file. So these are all my transition values, and these are all my input these are all my load values, and these are all my input transition values. So when the input transition value that the gate wants is 0.5, and when the output capacitance value according to that gate while optimizing, it is 0.05. So this value and this value. So according to the matrix form, it picks a value of 0.23. So I have circulated that value. So when it needs that particular value, it calculates from this particular table in the matrix format and picks a certain value. So lookup tables are nothing but where you have the transition information and the net capacitance information of that particular cell, with what range it has to calculate the delay value. So it is meant by lookup table. So these are the models or the NLDM nonlinear delay models, how a delay value is getting picked for an each and every cell. So the advantages of this particular linear delay models are it is basically very fast in the calculation. So the tool also is doing the operation very fastly, and the disadvantages is, if you can see, only minimal capacitances values or only single capacitance values are there at the output pin side. So this particular capacitances values of a particular cell are very minimal in number. So when you go to nonlinear delay models, that is a disadvantage. So where there are less capacitances values at this output pin of the cells. So that is a disadvantage, and loses accuracy beyond 130 nanometer. So when you go to when you come under 130 nanometer technology, it might or it might not show the accurate cell delay value of that particular gate. So it is less accurate when compared to other timing models. So this is the disadvantage of the timing. So from the cell delay calculation of the cell, as I discussed, we need to only calculate two values, that is the output transition and the propagation delay. So this is how we calculate the propagation delay that I have discussed till now. So this is what I discussed, how to calculate this cell delay of that particular gate. Now here I depicted it clearly. Now if you have a gate called inverter and input transition. So cell rise input transition is 0.1 nanoseconds, and my output capacitance is 1 picofarad. So 0.1 is in this particular range, so 0.05 and 0.01, and my load is in this particular range. So this particular table is needed to pick a delay value of that particular inverter. So using interpolation, that is again a mathematics background again, using interpolation algorithm and all, the tool calculates the cell delay values upon this transition range and the capacitance range of that particular cell. So in the same way, if the transition is fall, you need to calculate it from the fall table. If the transition is a rise transition, you need to calculate from the cell rise table. So the output transition at the pin, we are not getting it again from the manual calculation, it is also again depicted from the file itself. So with for the respective input transition, what will be my output transition for the given load, this also will be there in the transition tables. So the value is again interpolated and picked according to the gate. So this is how the transition values and delay values are picked in the nonlinear delay models. So the other current source, like the other timing model where we are using usually these days, is the concurrent current source model, and or it is also called composite current source model. So here they took an example of the current, the current waveform, and they try to depict the multiple capacitance values at the output side, so that they get an optimistic delay value for that particular cell. So the driver model is based on nonlinear current source, and the receiver model is based on the changing capacitances. As I told you, the disadvantage of nonlinear delay model is it will depict only the delay values for less number of capacitances values. But when the load is more and when the capacitance of that output pin is varying very randomly, in such cases your delay value also will be varying for that particular cell. So using this current timing source model, we can calculate that delay values with multiple changes in the capacitance values. So the advantages of this is the delay values are having better margins, so it will have an pessimistic or optimistic value when you calculate the timing information in a timing path, or when it is coming in a timing path in this gate level netlist. So essential under 130 nanometers, so it is used very probably in the lower technologies, that is less than 130 nanometer technologies, and disadvantages is requires many more delay values. So as I told you, it will be complex when you are calculating with respect to multiple transition values and multiple capacitances load values. So it's again a time taking process. When you consider this concurrent current source model, you have to calculate, or the tool needs to be calculating in multiple sources. So it's in such cases the runtime might be more. So basically this all is already automated in the tool. So the tool algorithm is automated such that it has to pick a value, it needs to do the process of interpolation, and it has to pick a proper value which is suitable for my timing. So this is the difference between NLDMs and CCCS. As I told you, single values of capacitances or some fewer values of capacitances will be taken in the NLDM, that is non-linear delay models, and the slew tables will be having minimal values, that means minimal delay values, that is for one transition value and one capacitance values. This will be my delay value. When you go to concurrent current source models, there will be multiple capacitances values, if you can see. So for each and every capacitances values, now the delay values also will be multiple. So this is again a time taking process. As I told you, the input slew values will be there and output slew will be projecting a values in a waveform. So if suppose the receiver model is having only two capacitances values here. Now, if you take a composite current source output, you will get a delay values within this range. So all the values within this range of graph can be taken as a delay value of that particular cell when you consider a concurrent current source delay model. So it will be in a way like too complex when you are considering this CCS. So there should be some connections present in the gate level netlist. So here I just took an example where the AND gate is connected to some buffer. So this particular netlist of circuit is there in your gate level netlist, if suppose. So there should be a net which is connected to that particular cell. So this net, whatever is connected, will not be ideal. Obviously it is a physical parameter, it needs to project some resistance and capacitances values when it is coming as a physical information. So where do we get that information from? So there is an option in the library models, that is the wire load models, how much resistance and capacitance is depicting, it is using when there is such fan out. So here if you see, the fan out is 1. That means for the AND gate, the output pin is connected to one cell. So if my fan out is 1, the resistance value it has to take and the capacitance value it has to take will be taken from the wire load model tables. So this is again a part of library. Anyway, in this wire load models, at the synthesis stage, we are just taking it as an estimation, because if you just take an example of a chip, now I have a gate, like I have a buffer, it is having an output of some 3 gates. So my fan out is 3. Uh, for this, the resistance and capacitance value it will select is 0.02902, and the capacitance value it will select is 0.01312. But when there is a gate, here and it is connecting with a huge net to the other gate. In this case, the fan out is 1, but the resistance and capacitance values are different because the net length is more. But when you consider this circuit which has fan out of 3, the resistance and capacitance values are depicted according to the fan out table which is there in the library. But what about the case where when there is only one fan out, but the net length is huge? In such cases, there will be wrong estimation done by the tool while selecting the wire delay model or the resistance and capacitance value of that particular cell. So that's the reason at the synthesis stage, the wire load values or the resistance and capacitance values of a particular cell or a net is taken as an estimation itself. When you take it in a form of physical, when you go to the later stages, that is when you go to physical synthesis, at that particular point of time, you can use this exact resistance and capacitance table. So, but as of now, in the logical synthesis stage, it is just an estimation resistance and capacitance. So that is what I have written here. The wire load model is used to estimate the effect of wire length based upon the fan out, and it is given by, and it gives an output of resistance and capacitance, obviously the area of nets. So the synthesizer uses the physical values to calculate the wire delays and the circuit speeds. So it just gives the estimated calculation of the resistance and capacitance values of that particular cell. So this is also called as RC parasitics, that is resistors and capacitors. So this is how the library timing model looks like. So here OR2, I have took an example of OR gate, that is 2_3, that is 2 cross 3, 2 input and 3 drive strength. That is nothing but it can handle a load of 3 gates, and the area it is going to occupy is 8 micron meters, and the pin description, the direction is of that particular Y pin is output, and the timing information. So based upon what the output varies. So my Y output varies according to A. Here, according to this gate functionality, my output is varying with respect to A pin. That is the reason they have given the related pin as A, and the timing sense is positive unit. That means the rise transition is happening at my A pin side. So positive unit is the rise value, and if it is a negative unit, that means a fall transition is happening at my input side. Now the rise propagation, that is the rise delay values in the matrix form, and the rise transition, that is the output transition values of that particular cell. So what is the functionality of that cell? So when given some input and out, when given some both inputs A and B, what is the functionality it has to perform? So it has to perform OR operation, that is also mentioned here, and the capacitances values. So min capacitance and max capacitance. The range of the capacitance values is taken in this particular area. So this is how the library model looks. And here for the execution also, we are using this particular delay models itself. So this is again an example of buffer, which I took a reference from our particular library. So the area will be defined in the same way. The pin description, the functionality of a buffer is again whatever is given at the input should be by output. That's the reason the functionality is defined as A again. The timing and the related pin is again A, because according to the input only my output changes. And the timing sense is positive unit. So according to the transition, whatever you are giving or the slew you are giving at the input pin, that is defined, and the delay table. Obviously, the range of values where it has to pick. So here I took a range of 7×7 because our library presently is supporting the 7×7 matrix operation or the interpolation operation while picking the delay values. So according to that, that particular table will be there.
Excuse me, the delay based on which methodology? Whether NLDM or CCS, how we can consider?
So that's what we, as I told you, if you take an NLDM model, there will be fewer capacitance values. So the capacitances value will be minimum. That means it will be a 1 or a 2 value, or a range like this will be specified. So
Okay.
max
How
and
we,
min capacitance.
no, based on gate, how we can choose suppose here some buffer. For buffer, what we have to choose? NLDM or CCS? How we can?
No. So totally a library file will be given to you using only one model. So the library file,
with all the
whatever.
delay values also. Is it?
Yes.
Okay.
So in NLDM, you will be having this maximum and minimum capacitance values because you have minimal range of values in the capacitance. So, but in CCS current source models, you will have a capacitance table also. So you'll have a different capacitance table. So by that you can make it out. It is a CCS model or an NLDM.
Okay, here index 1, index 2 indicates only for different delay values, right?
Yeah, index 1 is transition and index 2 is capacitance value.
Okay, fine. Yeah. Okay.
I have one doubt.
Yeah.
Right now you're showing CCSN model or what? The example?
No, this is also NLDM, but this I took as a reference of our library, whatever we are going to execute in the lab. It is also an NLDM model itself.
But I think the cap table will be there both in NLDM and for CCSN, I think, right? For different load tables.
So as I told you, in the NLDM, you will just have a maximum capacitance value and a minimum capacitance value for that particular pin. You will not be having a table. You will just have some few range of values for the capacitances. But when you go to CCS, you will be having multiple table values for the capacitances and output capacitance itself. So, but with a descriptive way of values, here they have took values of just C1 and C2. That is one range. C1 is my maximum range and C2 is my minimal range. But when you come to driver model of CCS, multiple variations of values in that particular graph will be taken according to that. In between values, that and all what are there in between range of that particular graph will be depicted in that particular table.
This table, whatever you are telling, this is for cell delay, right?
Which one?
NLDM and CCS. Right now, whatever PPT you're showing, slide.
Yes, it is for cell delay itself, but you can see the receiver model capacitances changes. I'm telling C1 and C2.
I understand.
Yes.
This is the difference of cell delay. But there, I'm asking the max cap and max tran value. This is different and that is different, right? So there I'm asking.
Okay, so that
You
is
told
what
the
I'm telling.
table
Like
will.
it will be having multiple tables. See, if you see this graph. So I took just an example for this graph. So I have some certain range. It is starting from 0 and it is depicting to minus some 0.5, and it is again coming back to 0. So how many values it is getting transited while it is moving through this curve. So that and all capacitances values will be there in this particular table. So for each and every cell we can't predict because that is already given by the foundry itself. So we can't predict how much the table range will be. So that is again given from the foundry itself. Is it clear?
Got.
Yeah.
Got.
So this is the input file, that is the library file description of a particular cell. So any queries regarding this, I'll address.
Here, what is values?
Okay. So
Index values. Index 1, index 2.
Is the list of input transition values. Index 2 is the list of output capacitances values. So if my value is 0.08 of input transition and I have an output cap value of 0.01, what is the cell delay value it has to pick? That means what is the propagation delay value that particular cell has to pick will be taken from this values table. So the value is 1 cross 1. So first value of that particular table will be taken. The delay value.
So which delay model we are using, where it will be mentioned?
That's what I told you, right? While opening the file, while you are opening the file, seeing the capacitances modules, you can just make it out as an NLDM or a CCS model. So it is again given by the foundry. That's the reason you need to open the file and just see that, like, what are the capacitance ranges and all.
Okay, fine. Yeah.
Yeah.
Yeah. Thanks.
Yeah. So let us move on to the next input file. So the first input we have discussed is the library input. So to convert it into a gate level netlist, you need to have an RTL module for which you want to convert it into a gate level netlist. So the other input we are considering is a Verilog design. It might be of .p or .VHDL. And some guidelines you need to follow while writing RTL. These are in perspective of the designer as a backend engineer or a synthesis engineer. You just have to have a knowledge which code is converting it into a which gate. But these are the steps that have to be followed when you are in the stage of an RTL designing stage. So these are some few steps. So you have to understand the hardware before the coding. So once you are coding a design, you need to think what will be the gate conversion of that. So according to that, if you are writing a RTL, it will be easier for the synthesis tool to convert it into a gate. So think the topology of the logic. So you need to think the topology, like from where it is arriving, where my input is getting connected, for which gate, what is the input will be going on, and what is the output it will be connected. So that topologies and all, you need to think before only while designing an RTL. Now, next is think synchronous logic. I discussed before in the ASIC flow also. Here we only perform synthesis, or we only do timing analysis for synchronous designs itself, because in asynchronous designs there will be this metastability issues or the data transfer issues. It will not reach the data properly, or there might be some metastability issues. That's the reason the whole chip or the whole module, whatever you are writing, the logic should be written in a synchronous logic form. So think register transfer logic. So whatever sequential logic you are writing, the register format will be should be proper. That means whatever clock parameters you are writing for a particular module should be proper. So synthesis tool cannot fix poorly coded logic, as a synthesis tool only handles synchronous design, and only some few parameters are allowed in perspective of coding. So you need to think whatever I'm writing as an RTL code will be converted into gate level netlist or not. In that in that perspective, you need to write an RTL code. So these are some examples where you can see the hardware interference of that particular logic. So if I write an if loop, so I'll get some adders. So in the same way, or else if you can write the same logic in both the ways. So these are some examples when you are using an if logic. So these are just the pseudocodes while you are converting into gate level netlist, which code will be converted into which gate. So once the tool access is given to you, you can try out writing this particular codes so that you can see the hardware interference or the gate level netlist of that particular logic. So if a case statement is written, you will get a mux, that is like they have given, because the 4 conditions, you need to have some 4 inputs. So that's the reason it has chosen a mux. So when a case statement is there in your RTL code, it means it gives an output of a mux. Next, here I have written some encoder logic. So your encoder, like it is a nested if else, that is if else if else. So when you have some logic like this, you will be having some combo logic. So there's a question, how will we know which code is converted to the netlist? So that is again from the experience you get. You write some code, you give it to the tool and see what type of gate you are getting. So it is again a experience itself. So if you have a for loop, you get some combo logic as such. So these are all the examples when you have this RTL code. So you can just make a note so that you can use these logics and you can use them in the lab exercises. So apart from combinational cells, you will also have some adder circuits and multiplier circuits also. So in the gate, I mean to say in the library. So if there is some RTL code in your, RTL file, so this kind of adder circuits will be given as an output. So these are some arithmetic circuits. In the same way, it will parses the expression from left to right, and parenthesis will override this default order. So if you see the first circuit, if you are writing some RTL code for the same Boolean expression, it is using gates in this format. A multiplier and plus 4 adders. So you need to think in an optimized logic. The RTL designer should be writing the RTL in an optimized logic format. So they can use this circuit so that they feel if they can reduce the gate count, they can reduce the area count. In directly they are decreasing this delay values also. So these are just the examples how the Boolean expression is converting into multiple gates. So this is again for sequential circuits. So if there is a flip-flop logic, how do it select a sequential gate?
Shravanti, just let me add a couple of points here. See, couple of slides what you are going through is related to the Verilog codes and then what this code gets translated to. Actually, the intention is you know what circuit to realize, then you use Verilog code in order to realize that circuit, whether it is adder, whether it is multiplexer, whether it is priority encoder, so all these, you know what you want to implement, and then you are writing code. So here, why we are going through in the synthesis session is, finally, your intention should not be beaten with a wrong Verilog code implementation. So that's where a couple of these, you go to next asynchronous, synchronous reset, Shravanti. So couple of very important things is how, whether in the circuit you wanted to implement the synchronous reset or asynchronous reset, both will have a different, functionality. So for example, here, if you look at the code, always at passage of clock, and then here, so you see what is the difference? Sensitivity list, there is a difference, right? And in asynchronous, in synchronous reset, right, only the clock we will include in the sensitivity list, and in sorry, this has got interchanged. So this is basically, this is synchronous reset, this is asynchronous reset. Okay, as in asynchronous reset, whenever reset changes also, right, I enter the procedural block. So like this, the way how you code, for example, you wanted to implement an asynchronous reset, but you have missed adding this in the, or the designer has, missed adding this in the sensitivity list. So then it will become, synchronous reset implementation. So that is, those are the kind of things which will happen in your coding style. Okay. So go to next. Next slide. So, and here also, yeah, blocking, non-blocking, you can keep. So here also, if you look at the way here, okay, See here, instead of here we are using blocking statements and here non-blocking. Okay, so basically your intention is to implement two flip-flop structure, right, with the clock, right, basically double synchronizer kind of circuit. So but when you are coding Verilog, if you use blocking statements either by mistake or not knowing, right, then what happens, right, the circuit, what you will realize, you see what is happening here, the D input, right, it is the same fit to both the flip-flops here. Okay, but that is not what you wanted to implement. You wanted the first flip-flop output to come to the second flip-flop input. Okay, so of course both the clocks are connected to the single clock source. So but with this mere way of coding, you see the different hardware implementation. So this is fatal. For example, now this is a wrong implementation which you didn't intend to get the when you synthesize, this is not what you wanted. With this, what happens, the functionality will go for toss, right? So those kind of things, right, if you know as you are a synthesis engineer, right, it will be good. Okay, yeah, next slide. So similar things, right, you can look at even for the so few more examples given here. So blocking and non-blocking, how the circuit will be behaving actually. Okay, so yeah, next slide. So just I'll walk through this Verilog part, Shravanti, so after that. See, that is where Monica, the Verilog session, right? We are covering the prerequisite we have put for Synthesis TA is that people knows Verilog. So now people doesn't know Verilog, whether it is function, task, then the coding style, the module, always, initial, or assign statements. All these, right? If you don't know Verilog, it will be little bit difficult. Otherwise, by the flow you will get to know. But non-blocking, blocking, those kind of things, if you don't know, it will be difficult to address here. But still, I will explain since you have asked. Blocking, go back to that blocking, this one, Shravanti. So I'll explain for the benefit of that. Okay, so keep this here. It's okay. So blocking means, right, blocking most of the time we use for modeling combinatorial circuits. Okay, that's one point. Okay, the next point is when you are executing the code, right, inside your process, this is a procedural block. Always block and initial block we call procedural. Procedural means what? It executes line by line. So now when it is executing this, when you have put equals, this we call blocking. Blocking means now before it goes to the next line, okay, now it will completely execute this line and the result will be available to you here. For example, now F, it will evaluate x1 and x2 and get output assigned to F output, output, and this F is available here, right? For example, this is x1 is 1, x2 is 1, F is 1. Now this 1 is available here for G when it is evaluating. Okay, so then let us say x3 is 0. Now 0 or 1, G is 1. Okay, so now this is blocking. What it means is it will, it is immediate assignment. It is immediate assignment. In non-blocking, what happens here? I have used non-blocking here. So this is the symbol what we use in Verilog, less than or equals. So F is x1 and x2. So same 1 and 1 you take, it is evaluated, right hand side is evaluated, and it will assign to the left hand side only at the end of the time unit we call. Now until it executes the complete begin and end, it will not assign to the left hand side here. For example, now this 1 and 1, then you may ask what is that F will be having. Now it comes to G. Now F or X3, let us say X3 is 0 is what we assumed. Now F is the previous value, whatever it was assigned with. Let us say F initially it was having 0, okay, and 0 or with 0, G you will get 0, okay, and when it will get updated, now here at this point in time, end of this, it will update the value of F. See, it's already evaluated. X1 and X2 is evaluated, but the assignment to the left hand side variables happens at the end of the time unit. Okay, so now with this we are solving race conditions, and also this modeling is whenever we want to model a flip-flop, we use this kind of non-blocking assignments. Okay, so that is the basic part. So no more Verilog questions, otherwise we'll be spending more time here. So that is where here with this equals, what happens in this circuit? See here, now F is X1 and X2. X1 and X2 is what? This AND gate output. AND gate output in here, it is directly going to the F, and then G is F XOR F or X3. Okay, so G is this F means what? This is AND gate output, and then OR with this, and this is the one. Now if you put non-blocking, you look at here, OR gate output G, and now this AND gate output is connected to D here. Okay, so that's how we can analyze this further. So that's the difference between blocking and non-blocking. So you will see a different implementation between the blocking and non-blocking. So actually here short between this, right, this OR gate, right, this is, you see the difference here. So instead of I getting F output to OR gate input, what I am getting because of the blocking statement, I am getting directly the AND gate output directly fed here. That is wrong. Okay, go ahead, Sean.
So these are some supportive constructs where a Verilog is accepting, the tool is accepting. So usually the Verilog constructs also will have this IEEE standards. So basic tool, whatever tool now we are using is having this particular standard of like the range of standard, that is 1364 to 2001, whatever constructs are there in this particular standard, that keywords are acceptable by the present tool. So not all the synthesis tools will be supporting this particular range only. It depends upon the tool you are using. So basically the Cadence Genus tool, whatever now we are using, is supporting this range of constructs. Now, what are those constructs or non-synthesizable constructs? There are like whatever RTL code you have written, like whatever examples I have shown till now using the RTLs, those are like all the synthesizable constructs that you can use in your RTL or that an RTL designer can use in his code. But there are some non-usable constructs. That means you should not use them in your RTL, so that that particular word or keyword will not convert into gate. So these are those constructs. So assign and deassign. So assigning and deassigning, when you are assigning a and deassigning a value in the RTL code, that is not allowed. When you're assigning and your operation, that means your conversion of the gate, that is allowed in the synthesis process. So these are the list of non-synthesizable constructs, that is definition and parameter, disable, event, pull up and pull down. So direct structural model is also not allowed in the synthesis format, and force and release, fork join, macro modules and primitives and any tri-state registers, wait, forever, real time, repeat time, and values. So the delay values, the timing values when you write in the test benches, right? That and all is not allowed when you are writing an RTL. So if you can notice, whatever values I've mentioned in the second and third column is basically the test bench parameters or test bench keywords we'll be using. Those and all should not be written in RTL. Okay, so there are some constructs or there are some keywords where if you write them also it's fine, but the tool will just ignore that keywords or constructs. So these are that list of constructs. So in the test bench, if you remember, like while writing or while designing RTL, you'll give a value as ash delay, where you will be specifying the delay value of the clock propagation. So that delay value you can just ignore. And procedural constructs, that is initial, specify, this and all will be ignored by the synthesis tool. And this strength specifications. So as I told you, like you should not use any structural model, that is AND gate or gate and all will not be taken by the synthesis tool. It will just get ignored. And system task. So if anything that you are defining starting with a tick, that is asterisk or tick, you usually call in the keyboard, so that and all will not be allowed while doing synthesis. If you are mentioning in the tool also, I mean to say, if you are mentioning in the RTL code also, the tool will just ignore this particular keywords. So these are just the list of ignorable constructs in the RTL code.
So here one input, see most of you, when you say, Verilog provides more than 50% of the constructs which are not synthesizable. So what is not synthesizable means they cannot be converted into equivalent gates, equivalent digital circuit, right? So any of the timing parameters, right? And some display statements, monitor, dollar strobe, and some of the macros, right? All these, right, are not synthesizable. So that is where when you're designing, you should be, very careful, especially when you're writing RTL, register transfer logic. When you are writing a test bench in order to test, right? So that is okay. You are not converting into hardware, and then just it is a behavioral code. So that is okay. Okay. So where for the beginners, it's very important actually where they are unable to understand is this particular aspect actually. So Verilog for design and Verilog for verification. So when you're using for design only the construct, the subset of complete Verilog, maybe 40 to 45% of the constructs in Verilog, right? Those are the ones really are synthesizable, used for modeling, means hardware model.
So these are some coding tips like you need to follow, or an RTL designer should be taking care of. So the RTL should be of technology independent. That means you are giving any type of library or any type technology library. It might be a 45 nanometer, it might be a 14 nanometer, or any technology. That RTL should be having a caliber that it has to convert into a gate level netlist. So if you are feeding any type of library input, independent of any technology, it has to convert into gates. Next, HGL should be described in single synchronous circuit. As I told you, we only bother about synchronous logic. We should not have any asynchronous logic. That means all the operations, whatever you are writing in the RTL code, should be with respective to one clock. Next is you need to describe clock reset in the central logic itself. That means the top module, wherever you are defining, there only you need to give the clock logic and reset logic also. And you need to use a glitch-free mux for multiplexing two signals. So if you are writing some multiplexer logic in the RTL code, you need to take care of the inputs that you are giving at the input of multiplexer. That means you need to not give more number of inputs where it might show a glitch. That means the sudden change in the transfer of the data. So that and all logic you need to avoid. And you need to avoid this glue logic at the top level, when you are considering a top level, that means you are at an SOC level. So the module you are working will be this M1, and there were modules M1, M2, M3. As a top level RTL engineer, the RTL designer should be writing a minimal glue logic. That means between the modules there should be a minimal logic. So this will be given as a module to the module level engineer. So between logic, whatever is connecting between the two modules should be minimal. So that intermediate logic between two modules is called as glue logic. So for a top level engineer, it will be difficult when you are putting multiple logics in that interfacing part. So you need to take care of that as an RTL level engineer. Now ensure output modules are registered. So you need to declare as a register for all the outputs. So separate the pads, memory logic and the core logic. So that is nothing but there will be some memory logic that might be a sequential logic, and the core logic that is the operating or the functionality logic of your module, and the input and output logic should be segregated nicely in the RTL code so that it will be easy for the conversion. Pads are nothing but input output pins when you consider a top level. So use non-blocking or signal assignment to describe sequential clocks. So you can use a non-blocking because the data have to be depicted. I mean to say that it has to have this transfer of the logic properly, and it will be stored in that particular sequential flop when you're using non-blocking statements. So these are the different types of inputs. So next is the other input, that is the Synopsys design constraints file, where so till now we were discussing only about the cell delays. So when you get a netlist, it will have port objects also, that is nothing but my input pins and output pins. So you will be have to define the delay value of that particular input and output pins, and at what frequency my chip has to function or my module have to function. That and all values you need to declare in this particular file called Synopsys design constraints file. So it's an attribute. First, whatever we are defining, I'll list out the timing constraints. That is nothing but the generated clocks. That means the output like divide by circuits are there in your RTL code. In such case, you need to write a command or you need to write a constraint for generated clock also. And input and output delays and the minimum and maximum delays of that particular input and output ports. So you can ask me a question like this: the delay values of the cell pins are there in the library, but the port objects, like whatever you declare in RTL as input pins and output pins, that port delay values we are not defining anywhere in the library. So that delay values we are writing in this particular file called SDC file. Next are some timing exceptions. So these are all the optimization constraints.
Excuse me, what is input and output delay and IO delay? What is the difference?
Yeah, both are same.
Both are same only, no?
Yes.
Okay.
Okay. Now
You
the
mentioned
time.
it too, right? That's it.
Yes.
Okay.
So the timing exceptions are the exceptions. So there might be some paths in your gate level netlist where you need not perform a timing analysis for that particular paths. So there will be some timing exceptions in your gate level netlist also. So in such cases, you can mention this timing exception constraint also in your SDC file. And also some design constraints like clock latency, uncertainty, input and output like transition with what value it has to start off. So in the library file, there are list of 7x7 values of input transition and output load as a start starting value for a particular gate, with what value it has to start off picking the input and output transition. That values can be mentioned in the input and output transition value of SDC. So clock gating setup, clock gating hold, and clock driving cell, this and all also are some delay constraints. So when you see an SDC file, you'll get to know about this. And design rule constraints, those are nothing but the maximum number of fan out, maximum transition on net, and maximum capacitance value on net. So for a particular cell, you can limit. So I'm taking just an AND gate. You can limit the fan out of this particular gate by giving a constraint called set max fan out, and you can limit the transition value of that particular gate by giving a constraint called set max fan out, and the capacitance value, obviously when you're defining the fan out, the load also you can limit using these three constraints. And there are some other constraints also: area, power, logical assignments, and wire load models. So which wire load models and all that and all, you when you go to this physical synthesis, that time I'll be explaining it clearly. So as of now, it is just a file where we are defining our clock frequency and input and output delay values, and if there are any exceptions in your gate level netlist. So that and all timing information we are giving it to the tool in the form of file called Synopsys design constraints file. Basically, a gate level netlist will look something like this. So if you take a gate, so this and all are the which are in the cloud form are the combo logics. So this delay values will be there in the library file itself. So the sequential delay values and the combo delay values will be there in the gate level netlist. I mean to say the library file. But what about the input ports? This black color, the ports, whatever this delay values have to be defined in the SDC file, right? So how we are defining the timing value, how we are relating the timing parameter for that particular ports is we are segregating the complete circuit into 4 different parts. So while doing this timing calculation, we basically report this gate level netlist in this 4 parts. So the first is input to register path. So input to register only it will consider, the tool will consider. So we report from a register to register again, and register to output. And if there is no sequential cell in between input port and output port, that particular path is called as a input to output path. So the tool handles only 4 paths. One is it is starting with an input port and it is ending with a flip-flop. That particular path is called as input to register path. And when it is starting with a register and it is ending with a register, that particular path is called register to register path. And when it is starting with a register and ending with an output port, that particular path is called a register to output path. And when there is no sequential cell in between of input port and output port, that particular path is considered as an input to output path. So any gate level netlist, you take only this 4 paths will be there in the circuit. So there is no direct path from input. Yeah, direct path in the sense the path is from input port to register, right? So it will include the delay values of the combo cell also. When I am telling input to register, it will also include the delay values of the combo logic also. So how we are defining clock? There will be a team called a clock time budgeting team, where they define the clock frequency depending upon the module which you have implemented or which got manufactured before. According to that module, they define some clock frequency and start off this timing operation. So if you take a particular circuit, like if you have some circuit where you have some input port, output port, and a clock signal, and some flip-flops in between, and you have some combo logic. So the clock is defined using this formula called 1 by frequency, that is T clock to Q delay of the first flip-flop, and the combo logic in between, and the setup time of this particular sequential cell, and that is also again taken from the library. So this is again done by a team called time budgeting team, where they give the frequency according to the previous manufacturing of that particular module. So this is how an example of an SDC file looks like. So we define the clock frequency using a command, and this is like a user executable. Okay.
Shravanti, 1 minute. So all of you understand the basics of timing, at least setup time, hold time. So this maximum frequency, how do you determine the maximum frequency of a particular circuit? Any explanation required here?
Yeah, we can understand.
So this is the base,
Hello?
for synthesis and the timing analysis, which we will be doing further.
Hello?
So yeah, are
Hello?
you able to hear? Yeah.
Hello, sir.
Yeah.
Can you explain me why we need to consider input pin to output pin combinational path since it is not included clock, no?
No. See here, whatever example Shravanti is showing, there is a combo path. Okay. So if there is no gates in between, directly input to the D input, right? Okay. So at that time, the delay of the combo path will not be included. There is no combo. Okay. So basically, for the timing analysis, what are the different paths? Normally, right, it will be considered, and also the design. There will always be, for example, just input output. You look at, there will be input buffer itself in the IO pin, right? So that way there will always be, combo path along with. So this is the typical structure what you see inside the chip, inside the design. So there will be registers, flip flops, and in between there is logic. That is where you saw the Verilog code. There are a lot of if else statements and the case statement. All these combinatorial will be coming in between. Okay, so that is where just I'll spend 2 minutes to explain about the timing part. So in STA, anyway, it is part of our internship program, Synth STA. Every timing arc, input to reg, all this will be explained. Just the basics of this one I'll explain here. So if you look at how you are deriving, a particular circuit, it works in this frequency. See, all the circuits we want to operate at a very high frequency in gigahertz order. What is the problem, right? Why we cannot? Why a particular circuit will not meet the high frequency requirements, right? Those are governed by the basic the timing analysis, right? What is done in the ASIC design process. If you look at, so what is considered here is the synchronous circuit and the typical way how the design ASIC design is done, right? So if you look at, there is a clock and there is always this clock to Q. Okay, so in the slide, whatever you are seeing, there is always clock to Q delay. Okay, now that is one delay, that is TCQ. And what it means is whatever input coming at D will be passed to output Q after TCQ. So now somehow the D is shown here below, output is shown here. So now D, whatever input D is changing here after TCQ. Now at this point in time, Q is available and it passed through this delay, combo delay. This is combo. This is TCOM. Okay, this is TCOM. So the maximum time what you can have, for example, now here you have multiple levels of, let us say, some algorithm you have put in combinatorial, multiple stage of multipliers or something, right? Coming, this output has to go through. Then it can take as much as time it can. Let us say here this T combo, it is taking if you want to take some numbers, so this whole thing you can assume as 10 nanosecond, right? The clock period. So this is operating at 100 megahertz. Now so here the 10 nanosecond, let us say this TCQ is 1 nanosecond, and this TCOM, let us say it is 6 nanosecond. Now, here, this setup, what is shown is this one. Now, this flip-flop, before the edge of the clock, before it samples the data here, it expects minimum time where the data has to be stable, right? Now, that is the setup for the next edge. So now that is TS. Now, within one clock, you need to accommodate all the 3 delays. What is this one? TCQ, clock to Q, and combinatorial delay of this path. And this is basically I'm doing from reg to reg analysis, one path, one timing arc I'm analyzing. Now this whole thing has to happen within one clock period. For example, now TCOM got extended till here. What happens? We call this setup time violation. Then how you can fix this problem? One easy way is increase the clock period. Now 10 nanosecond is there, and then if you make it, let us say another 2 nanosecond, if you want to make it, right, 12 nanosecond. What happened? Now 100 megahertz you are running at, now because now you have delayed or you slowed down the clock. Slowed down means period you are increasing, then it is going beyond, let us say 150 megahertz, or your delay is so much that you have to increase 20 nanosecond, then this thing is it reduced to 50 megahertz. Okay, that is how, because your frequency is reciprocal of clock period. So that is how this setup, combo, and TCQ limits the frequency parameter. So this is the base of it, and basic for all this thing. The more we will, Shravanti will take you through in the static timing analysis. That is the intent. She's not spending much time here. So just the basics actually. So is governed by this, the synchronous circuit timing analysis. Hope you understood. So these are the ones. So now this is set up, and then here T hold, the minimum time it has to hold after the edge of the clock is hold, right? And so further it goes on. So we will learn more in STA. So because the slide was put, and then for some of you beginners, I thought let me explain. Okay, Sean, continue. Now there are many solutions. Don't worry. Right now I just said one of the way. Okay, there are other methods as well.
Yeah. So this is how the SDC file looks like. So create clock is the command for giving the clock frequency. So in terms of period we are mentioning, so the tool accepts in the nanoseconds form. So it's 2 nanoseconds, and the input delay value some 0.8, and output delay value according to the clock period they will be defining for input port and output port. So set input transition, that is the transition value of a port, and set load value, that is the load value of the output port we are defining here in the SDC file. So the delay values, the timing values of the port objects, and the clock frequency basically we define in a SDC file. Next is the outputs. So as we know, like the output, what we get is a gate level netlist, and then you get an output SDC also. I'll show the difference between input SDC and output SDC when we get into this tool flow. Then reports are nothing but we basically bother about 3 types of reports. One is timing, power, and area. So this is how the gate level netlist look. So you'll have a module. It will be in the format similar to the RTL code module, the input and output pins, and the wire connections are the net connections of the gate level netlist, and the gates that has got converted that will be there, and that particular drive strength it has picked from the library file. So this is how the gate level netlist look. So this is again a file format which we are going to check in the flow of the synthesis. So the output SDC looks something like this. So the timing report. So when you are checking a timing report from one register to other register, this is how the timing report looks. So I'll explain this when we do the tool implementation. And the power report, you will be basically seeing this dynamic, that is the switching power and the leakage power information when you do the power report analysis. And the area report, because you are in synthesis stage, you are not physically implementing it, you are just using that as a reference. You are just using that number of cells as a reference. So total instances, if you can see, total gates are 497. As you are not using them physically, the area will be 0 when you are in synthesis stage. So let us go to the cadence flow of Genus, by how to load the data and all. So first, the flow starts with loading the design data. That means you need to load all the technology inputs, that is your library file and RTL file and the SDC file. So applying timing constraints is nothing but you are reading the timing constraint file, and synthesizing design is nothing but you are performing 3 steps of synthesis, that is translation, mapping and optimization, and analyzing the results, that is your reports. So these are all the commands to give the execution format in the tool. So read library is the command to read the library file, and read HDL is the command to read the HDL file, that is your Verilog file, and
Shravanti,
elaborate is,
can you
yeah.
go step by step? Just display one at a time. Step 1, step 2, further better understanding. Just one by one you go. No, no. The commands. This is okay. Commands.
Okay.
Just
So
display.
according to the flow, first we need to load the design and the technology data. So the first step is we are reading the library file. The command to read the library file is read underscore lib and the library file name that you want to read. And you need to read the Verilog file also. So read HDL is the command for reading the RTL file and elaborating the RTL file. So if you have a module where it has multiple instantiations, so it needs to abstract or convert the gate level netlist into multiple modules. So in such cases, when you are converting the gate level netlist into lower levels, that means multiple modules conversion, you need to elaborate the design. So this basically is segregating the RTL code, whatever you have written, into different modules. And check design unresolved. So there, if you do this command, basically it will show if you have multiple RTLs. That means there is no one RTL in the top module. They have instantiated multiple modules, and you have forgotten or by mistake you did not read one of the RTL file or one of the module file. So in such case, it will throw an error. You can just check the module whatever you did not load, and you can just read that particular RTL file in read HDL command. So, okay, so elaborate is basically you are segregating the top module into lower modules. So if you have a top module, you will have multiple modules instantiations under it, right? So it is segregating the connectivity of each and every module to the top module. Next is constraint file. So you need to read the SDC file using a read SDC command. So read SDC and the file name. Next is you need to perform the synthesis steps. That is according to the theory what we have explained in the previous session. There are 3 steps in synthesis. One is translation, one is other is mapping, and the other is optimization. So this translation is nothing but you are converting the RTL code into Boolean expression. So that is taken care with the help of syn generic command. Next is mapping. So generic gates should be mapped to the library gates. So that mapping is done using the command called syn underscore map. And optimization is syn underscore opt. It will perform optimization. if we do not have multiple modules, only a top module. Okay. So in the top module only, if you have, like if you have to tell the tool to elaborate the connectivity between ports and the logic, right? So if you are having a single module also, the internal logical connectivity with the ports should be elaborated. So if you are having a single module also, elaborate steps should be performed. So next is you are generating the timing report. That is one of the report is report underscore timing is the command to generate the timing report. Next, you can generate the power report by using a command called report underscore power. And you can report the area by using report underscore gates or report underscore area. Also, it will show the gate count. Obviously, at this stage, the area will be 0 itself because we are not implementing physically. So this is the execution steps. So if this is clear, we'll get into the tool operation of the Genus flow Cadence tool implementation. So is this clear? Okay. Yes, I'll be discussing about the lint in the tool so that you'll get a clear idea. So here I just took an example of APB UART, that is Advanced Peripheral Bus with UART interface, that is Universal Asynchronous Receiver and Transmitter RTL code. Basically, it's used for the transmission and receiving of the bus parameters. Just give me a moment. Yeah. So this is how your RTL looks. So you can take any RTL, but as an tool flow part, I just took an example for this APB UART RTL. And so here for the beginners, I'm just telling if you are running, like when the tool access is given, the library file which you are going to use will be there in this particular directory called computer. So inside that you'll be having a file system one. So you can note down the path. You'll have a home directory. Directory is nothing but the folder. So inside home folder, you'll have a CAD folder. So where you'll be having all the Cadence related libraries and the tools. So you'll have CAD folder. So inside CAD, you'll be having a directory called Foundry, where all the Foundry related information, that is nothing but the library and the information which is from Foundry is given. So inside that, you'll have a directory called digital. So here you can see they are segregated according to the technology. So let us use the lowest technology we have. So I'm just entering into 45 nanometer technology. Inside this, you'll have libs, where you'll have all libraries, and lib. So here, as I told you, there will be different library files depending upon the different wire load models and different operating conditions you are working on. So here in this particular technology, they have defined two operating conditions, that is two process voltage and temperature conditions. One is maximum process voltage and temperature conditions, and the other is minimum process voltage and temperature conditions. So inside max, if you go, you will be having all the operating condition delay values of the particular cells is in the form of a file called slow.lib. So if you want to perform the synthesis for the minimum operating conditions, you can use a minimum library, that is the fast.lib. Inside the folder of minimum, you will be having a file called fast.lib. That one you can use when you are performing on a minimal operating conditions. So as of now, I am just showing you an example for maximum operating conditions. So here you will be having an option to open this file with an editor. So you can open with a gedit. So it's an user friendly environment as such as the Windows. So you can just open this file with gedit. So I am clicking on that file and I am opening it with a gedit. Okay. So if you see the format, what I discussed for each and every cell, the library description till now we have seen. First section will be your unit attributes. So the timing unit is in nanoseconds and the voltage unit is according to volts and the current is milliamperes and kilo ohms and the nanowatts and the capacitance is in picofarads. So for each and every cell, the values will be taken from this unit section. So this is how the library file looks. Let me show you an example of each one cell so that you'll get a clear idea. So I'm just selecting a cell called buffer. So I just took an example of a buffer cell. So the area it is going to occupy at this particular stage is 0 because we are doing only logical synthesis. We are not physically implementing that. That's the reason the area is 0 and how much power it is going to take and what are the pin attributes. A is my input pin. It will be known by the input direction and the input signal level. It should be connected to VDD to propagate that cell. And the capacitance values, rise capacitance and fall capacitance. You can see somebody was addressing the questions how we can make it out. It's a CCS or an NLDM. You can see here there is only one capacitance value and a range of rise and fall capacitance. There is no capacitance table for that particular cell, so we can make it out by this. So buff X12 is basically X12 drive strength, so it can drive 12 gates or 12 fan out at the output. So it is basically defining the drive strength of a buffer. So this is how the pin attributes will be there and the timing if you see such as the index 1. So if your rise transition is there, input transition and output load, this is a 7x7 matrix. According to the input transition and output load values, the delay values are picked from this particular table. In the same way, the transition, that is output transition of a particular cell, also have to be picked based upon input transition and output load values. So in the same way, the transition table at that output pin also will be calculated using this transition table, lookup table, that is again a 7x7 matrix. If the delay is fall delay, that means your transition and the capacitance are the falling delays. That means you can pick the value from the cell fall delay. In the same way, fall transition. So for each and every cell, this particular parameters will be defined for a gate. Any cell you can see, when you get an access, you can just enter into this particular file and explore on the different types of cells and different types of inputs and different types of drive strengths also. So I'm just closing this file. So this file we are using for the implementation of synthesis process. So one is the UART, that is my RTL file. The other is the slow.lib, that is the library file. And next is I need to have an SDC file. So I'll show the SDC file also. So this is how the SDC file is looking. Now in my RTL code, because there are two clocks, so I have two clock objects, one is PCLK and the other is PCLKG. We need to define the clock frequency for two clocks. So that's the reason we have defined SDC giving the frequency of the clocks So according to the spec we have got for APB UART, the clock frequency is 12 megahertz. So when 12 megahertz got converted into nanoseconds, it's just 83 nanoseconds. So that is how we have calculated the time period in nanoseconds according to the frequency. So we are defining clock frequency for both the clocks. Next, we are defining input delays and output delay with the clock objects. As there are two clock objects, there might be inputs which are propagating through p clock, and there might be inputs which are propagating through p clock g. So that is nothing but gated clock of UART. So we need to define the delay values for both the inputs and output clock objects.
Input delay, excuse me, input delay means pad delay or what delay that
Yeah,
is?
port delay, port input. If you are in
Pad,
RTL,
input port pad
yeah,
delay, is it?
yes,
Okay, okay. Input pad delay as well as output pad delays. Correct?
yes,
Huh?
yes.
Okay, okay.
Okay. Next is input transition and output load. So the input pin transition and output pin capacitance of the gates is defined in library. But what about the ports? So you need to define for the input and output ports also, right? So here we are defining the transition and load capacitance values of the input ports and output ports in the gate level netlist. So these are the list of files we are using for the implementation of the synthesis process. So is it clear till here, so that we can start off with the tool?
Yeah, where can we get the delay? Input delay and input delay, output delay.
So
Where can we get that info?
okay, so as I told you, according to my spec definition, my clock frequency was some 12 megahertz. So when I converted it into timing, that is nanoseconds, it is 83 nanosecond. So there will
Yeah,
be a
okay.
budgeting team that will be defining how much percentage you need to take as a input delay, and how much percentage you need to take as an output delay, how much percentage you need to be taken as transition and load. That will be defined in the specification file itself. So according to the clock frequency percentage, you can
Okay.
define the input and output delays.
Okay, okay, fine. And input transition also like that only? No?
Yes,
Input
yes,
transition also with respect to percentage they will mention in this spec itself. Is it?
yes, because it's the port delay. It is coming from RTL, right? We are not taking it from the library. It is like a user defined value. So we need to take it as a percentage from the clock frequency itself.
Okay, okay, fine. Understand.
Yeah. So is it in nano? As I told you, we are considering it in nanoseconds. The period, whatever we have mentioned here, is nanoseconds.
Okay.
Okay. So these are the list of files we are going to use for the implementation of the synthesis process. So I'll just enter into one directory called synthesis. You can create the directories also, but I have created everything. So I am just entering into the synthesis directory where I am going to implement my synthesis process. So here you need to invoke the tool. You just can't directly read the files as the tool is not pre-invoked. You need to just invoke the tool using some commands. Just make a note of this. So I am right clicking in that particular directory. So I'm right clicking that particular directory. I'll get an option called open in terminal. That means where you are executing the commands, you'll get into that particular terminal. So I am giving this open in terminal. Now, once you open a terminal, a window gets opened where you can execute your commands. So once you are entering, so is it clear? So shall I maximize it? Okay. So you will enter into this particular environment where you are invoking the tools. Okay. Now here, first you need to enter into a command environment. So CSH is the command where you will be telling the tool to enter into command shell environment so that you can give the tool commands. So CSH is command shell resource, command shell environment. So once you enter, you will be again coming back to the next slide. Now you need to invoke the tool. So to invoke the tool, there is already some predefined tool file where all the tools which you are going to function are already defined in that particular file. So that file you can use using the command source. Source is the command for just you are invoking the tool environment. CSH is just for giving the commands. You need to enter into command environment. Now you need to enter into tool environment. So I am just giving the command to source the tool. So source is the command and you need to define the path. So my path where all the tools are set is in this particular region, that is inside home. You have a directory called CAD, and inside CAD you have a directory called file called CSHRC. So where CSHRC is command shell resourcing, where you are sourcing all the tools. So once you give this, the path will be same for everyone. So source, home, CAD, inside CAD I have a file called CSHRC where I have the tools. Now once you give that command, you will get into an environment where welcome to Cadence tool suite will be visible to you. That means you are inside the tool environment. Okay. Now, once you enter this Cadence tool suite, you need to give the tool name which you want to invoke. As I told you, the Cadence tool for the implementation of Genus, for the implementation of synthesis is Genus. So Genus is the tool name for doing the synthesis implementation. So I'm just giving Genus. Okay. So once you give a genus and give enter, you will be entering into a genus tool. So it will take some time to load. Okay. So once you have entered this genus tool, you will be under this directory. So genus underscore root, and you'll be given an arrow to execute the commands. Okay. So clear till here how to invoke the tool and how to get into the environment. So this is basically according to the environment that you are getting the access I am showing. So, okay. So that there is nothing complex thing. First you need to give CSH, then you need to source the CSHRC file where all the tools are there. Then you have to give the tool name. Okay. Now, the first command that we are giving is we are reading the library file. So read underscore library is the command for reading the library file. So read underscore library, and you need to give the path of the library file. So where is the path of my library file I need to give? So I'm just giving a home. So inside home I have CAD. So you can just give tab on your keyboard so that it will show what are there inside CAD. I mean to say inside home. So inside CAD, if you want to know what are the things, you can just give the slanting line and you can just give tab so that it will show the contents what are there inside the CAD directory. So inside CAD directory, I want to enter into Foundry. So I just have to give F and give tab on your keyboard so that the complete path comes. Inside Foundry, I have digital where I am going to use the digital libraries. And inside digital library, I am using the lowest technology which is available. So 45 nanometer. In the same way, you need to give the tab every time so that you can get the complete name. Inside 45 nanometer, you have a path of libs. Inside libs, you have a directory called lib. So inside lib, you have two different types of libraries. You can use either of the libraries and see the timing changes and the power changes. As of now, I'm just explaining you guys with the example of maximum library, that is the worst conditions, the worst delay conditions or the maximum delay conditions. So inside max, I have a file called slow.lib. Yeah. So this is the file I want to read. So you can note down this path. So read library is the command, and the path of the file you need to mention in this command. So once you have read this library, it will show it is reading the library, and it will show some set of warnings. It is just showing you are assigning 0 value to that particular cell. It is okay. You should not get any errors. You just have to get warnings. Warnings are ignorable in this particular stage. Please mute it from your side. I am able to see the disturbance. Listen the disturbance. Okay. So once you have read the library, you can see some. Yeah.
You can open the whatever file, right? So can you
Yeah.
open that file, keep it on the left hand side, and then execute the command one by one. So that will be helpful for them to understand that what step we are executing. So all these steps, right? So we normally use scripts, and then we have put it in run.tcl. For your understanding, Shravanti is taking you through command by command. Basically, so these are the things actually what step by step she's executing. Shravanti, I think you just walk through this and then run the script for today, because it is getting delayed. And tomorrow further, if there are any doubts, we can address that. In run.tcl, you just explain what are the steps, like already we have explained in the PPT also. So these are all the commands we have put, and then these are the variables we are giving. This is the design, this is load.lib, and then this read SDC, this SDC.SDC, right? And then finally generic map opt, and finally write HDL. So this is we are writing out the netlist and writing the SDC. So this script she will run now, and for today we will stop there. Maybe output one of the report you can show to them, or netlist file we can show to them, and then further we can continue in the next session, Shravanti. We don't want to hold them for long.
Yeah.
So 8:50
Okay.
sharp, another 5 to 6 minutes, we will close it.
Yeah.
Yeah.
So here in the run.tcl file, if access is given, I'll be sharing this file to you guys also. So here I have put the industrial flow, but as a beginner, you can just read the library file using this particular command called read_libs. If not, you can just read the library file using this command also. You can set an attribute of the path where your library file is, and then read that particular library file using this slow.lib command. So I have done already this step. So next command for the reading the RTL, right? So read HDL is the command for reading the RTL file. So I'm just reading the RTL file. Read_HDL is the command. So I have my HDL file in the root, that is which is on my desktop. So in the desktop, I have a file directory called apbwat. Inside that, I have a directory called RTL. Inside that, I have the RTL file. So I'm just reading that file using this read HDL command. So once this is read, if you are having errors in your RTL file, it will show here itself. So read HDL is basically for reading your RTL file. Once you are reading your RTL file, you need to see or you need to elaborate the design. That means you are connecting the functionality with the input and output pins which are there in your RTL. So elaborate is the command for elaborating your design. I'm just giving elaborate. Now, once this is elaborated, you will get there is elaborating this block, that is UART block. Under this, these are the some warnings, unreachable case statements. It's okay at this point of time as a beginner, you can just ignore the warnings, because RTL defined whatever I have took is just an internet source. So you can just ignore the warnings. Now, once the elaboration is done, the thing is you need to check design unresolved. So you need to check, did you need to check, did you load the RTL files, whatever you have mentioned properly or not. So I'm just checking unresolved, check design unresolved is where you are checking whatever modules you have instantiated in the top module are covered properly or not. Have you read properly or not? As of now, we are only having one RTL file. So there are no submodule RTL files. If in case you, like when you are writing your own RTLs and you are instantiating modules in different RTL files, you want to include all the files. In such cases, you can just give check design unresolved and it will show the list of RTL files which you have not read. So as of now, there is only one RTL file. That's the reason it is showing no unresolved references. That means my RTL is clean and I can go forward. Next, once you have done this, you can read the SDC file. That is my next input. So read underscore SDC is the command. So in the run.tcl file also I have mentioned. So I'm just copy pasting my path of the SDC file. So read SDC is the command for reading the SDC file. I'm pasting it here. So read SDC, I'm just reading that file. So now my success, whatever commands I have given in my RTL file, if there are any, in the SDC file, if there are any issues with that commands which I have mentioned in the SDC file, that will be shown in this particular read SDC command report. So as of now, my failed things are 0. All whatever commands I have written in the SDC files are successful. The failed are 0, so I don't have any issue. I can move forward. Next is whatever timing information in the library you have given, you have written SDC and you have written RTL. So if there are any mistakes overall in this particular files, so there is a command in between where you can do report timing -lint. So you are performing linting check using this command. So report timing lint is basically a command where you are checking the linting check, that is whatever information you have given in the SDC file is proper according to your RTL. So for the RTL you have read, for the SDC you have read, if the RTL is having any unsynthesizable constructs and whatever SDC you have given, you did not define that particular things in your RTL. So it will link both RTL and SDC and check the errors of that both files. So this is the report of the RTL. So you can just do like a description of that particular. Once this is done, I will show the linting check report again. So report timing lint is basically checking the syntax of your SDC file and if there are any unsynthesizable constructs in your RTL file. So report timing lint does that. Once this is done, you need to enter into the process of synthesis. The first step of synthesis is you are translating the logic. So for the translation of logic, you use a command called syn_generic. That means you are converting the RTL code into generic gates. That is, you are translating it into a Boolean expression format. So it has done Boolean expression conversion and it has converted into some generic gates. So you need to do write HDL to see how my gate level netlist looks at this particular stage. So write HDL is the command. So if you can see, it has converted into some basic gates. It did not convert into library gates. Okay. Now, once you are converting it into generic gates, you need to map it to the library gates because I have given a library input where all my gates are present. So syn_map is the command to map it to the library gates. So it is showing done mapping. Now again, let us do write HDL command so that we can see how it has mapped. So before and all, it was having just inverter, NOT and NOR. Now you can see it has picked a gate which is there in the library. So it has picked some drive strength which is already there in the library. So this is how the mapped gate level netlist looks. But this might be a finalized gate level netlist, or this might not be a finalized gate level netlist. So that we'll get to know with the step of optimization. So we'll generate some reports at this particular stage so that we can make it out the difference between mapping. So report gates is a command. Report underscore gates is a command for giving the gate count. So you have total 594 gates and the area is 0 because we are not doing any physical implementation. And you can give report underscore power for a power report. So this is your leakage power and this is your dynamic power, that is nothing but my switching power. So for these many gates, the cell wise power, if like the power totally used by that particular 594 cells will be given in this particular section. Now these are the reports once you have done after mapping. Remember the gate count so that you can see the difference after optimization. Now it has mapped to the library gates. Now we'll see once if it is doing optimization, in what way it is optimizing. So syn underscore opt is the command for optimization. So it is optimizing, taking the SDC file in form of timing, power and area. So again I'll do report underscore gates. See, now it has optimized some 100 gates. So before after mapping, the gate count was some 597. Once you have done optimization, it is reducing the timing, power and area, and it is considering the area into consideration, and it is reducing the number of gates. That is, it has reduced approximately some 100 gates. So in the same way, you can report the power also. Report underscore power. So the dynamic power and the leakage power also got reduced. And there is one more report that we need to generate, that is timing. So report underscore timing is the command to generate the timing report. So this and all timing report, you can get a clear idea when we enter into STA. So as of now, it is not so required. So we'll just discuss this timing report part in the STA session so that you'll get a clear idea there. So the three commands is basically report timing, report power and report gates. So these three are basically report commands we are writing out. Now, write HDL is the command to write out the gate level netlist once after mapping or once after optimization. So write underscore HDL is the command to write out the gate level netlist. So it will display in the terminal. Now, if you want to save this file, if you want to dump this file, you can just give write underscore HDL and use a greater than symbol, and you can give the file name. I am just giving UART underscore GLN, that is gate level netlist, and with an extension of .v I want to save it. So write HDL with whichever I am dumping it in UART gln.v, whatever write HDL command is executing, that gets dumped in this gln.v. Okay, this is how you dump the files. If for all the commands, you can use this arrow mark and you can give the file name so that whatever reports you are generating, you can dump in a particular file. So I'll just open that file and show you. So to open the file, you can use the GUI, or there are commands to open the files also. So I am using an editor, that is gedit. I want to open UART gln file. So I'm just opening UART gln.v. So this is how your gate level netlist looks. So all the inputs, outputs and the gates that got picked from the library for your particular RTL code. So this is how you generate the gate level netlist. Next is another file, that is SDC file. So write underscore SDC is the command to generate the output SDC file. So write SDC I am giving over here, and I am just giving output OP underscore some file name you can give, specifically not only this name, you can just give any of the name SDC, and the extension of the SDC file should be .sdc. So I am dumping that particular SDC file. Now let us see what is the output SDC file. So if you can see, in the input SDC file, we have just given all inputs and all outputs. We did not mention each and every input. In the output SDC file, whatever you have mentioned for each and every input and output will be assigned to each and every input and output port of the RTL. So it will display, or it will assign that value for each input and output port. So you can see the difference between input and output ports as such. So this is the flow of synthesis. So it is done. Any queries I'll address, or else let's end the session.
Hello.
Yeah.
Yeah, that generated SDC, that output SDC.
Yeah.
Next time we can give this SDC as a input, or this is just for major purpose? We can
This
just
is,
check it.
yeah, this SDC you will be giving to a PD engineer.
Okay.
So that person will be taking this SDC file as an input while he's implementing physical design.
And one more thing, that lint report, actually I want to follow, then the same procedure should I follow the right lint or something, that command less than or greater than symbol?
So the command in the Cadence is report underscore timing hyphen lint. So the same command you can use when you are implementing also.
For dumping also I can use the same thing. It's greater than sign.
Yes, greater than symbol and the file name where you want to dump.
And if I will write down, like you show me that run.tcl file, that file contain all the these commands. For that I will like I want to run this file in a single shot. So I will just write down is read and then tcl. That is fine.
Yes, yeah. You have to dump like whatever I have executed in the terminal. You just have to dump all the commands in a single file and just give source this file. You can run the complete file.
Okay. Super. Okay. Thank you.
Yeah. So this is one method. So as you guys are asking me, like at one time how you can run is, so I'm just exiting the tool. The same process until you are entering the tool. Just invoke the tool. And already because the commands are there in run.tcl, I just want to run the file giving all the commands in a single file. So you can just give a command called source run.tcl. So it will execute all the commands which are there in the tcl file. So the command file, tcl is basically a tool command language where the script, it is one of the scripting languages. The tool accepts the commands using that format. So everything it has done in a one run. Okay, more any queries?
Hello, madam.
Yeah.
Ma'am, just wanted to ask, these tcl files or SDC files, like these are normal text files?
Sorry, Shravanti, we will not take questions in the next session. See, we are already 40 minutes, we are delayed. So whoever were asking question, I don't know the name. So we will address those queries in the next session.
Okay, sir. The next session.
Because some people are really concerned about the time. So we will try to keep up our time 6 to 8. In case it spills off, 10 to 15 minutes we spend extra. So beyond that, we don't want to really take more time, actually put you in inconvenience. Okay, thanks everyone. Thanks, Shanti.
Yeah.
Thank you, Sravanti.